Yeah. To discuss about reliability testing and data analysis, which is a crucial topic in advanced engineering system, especially in related to the advanced reliability. To be honest, this section has a lot of very complicated equations, but I guess that this equation will be so useless if you are not using in the future. So that's why I prefer to just give you initial, the basic and fundamental things about the topic, and then if you are using in the future this method and this concept, you can use the appropriate formulation related to your applications. Okay, in this lecture, we will explore how reliability testing helps us evaluate the performance and durability of systems under various conditions, and how data analysis techniques allow us to interpret a test result effectively. And we will also discuss different testing methodologies, failure models, statistical tools, and how data-driven insights can improve system design and predict future performance. At the end of these sessions, hopefully you will have a clear understanding how to assess reliability and make informed decision making based on the analytical results. All right, in this slide, I just wanted to present the outlines of today's lecture. Uh, our main objective is to explore various reliability testing methods and to develop a solid understanding of data analysis techniques used in this field. Reliability testing plays a vital role in ensuring the performance of products and systems while reducing the potential failures and associated risk. Throughout this lecture, we will cover key topics such as accelerated live testing, ILT, effective test planning, proper data collection, and different methods of data analysis. But generally, data-driven methods, big data, data analysis, pre requests of analysis and, and data are very important part of the each all of your research. Additionally, this session builds open concepts from previous lectures, particularly reliability modeling and probability distributions, and helping you connect theoretical foundations with practical applications in reliability engineering. All right. Uh, we have another section, section two. I want to introduce the fundamentals of reliability testing. I begin with by defining reliability testing and explaining its primary purpose, which is to assess how a product or system performance over time under specific conditions can be developed. Next, I explored different types of reliability tests, including live testing and environmental testings, as well as the distinction between destructive and non-destructive testing methods. We also compare field testing with laboratory testing to better understand their respective advantages and limitations. Key reliability metrics such as mean time between failure, MTBT, BF, and failure rate are also already introduced, but we can refresh here again, along with the discussion of common failure mechanisms. Finally, we emphasize the importance of reliability test standards, which help ensure consistency, accuracy, and credibility in the testing process. All right. In this in section 3, we want to focus on accelerated live testing, ILT, an essential approach in reliability engineering. We want to begin with an introduction to ILT and discuss why it is widely used, particularly for saving time and reducing testing costs by accelerating failure mechanisms under higher stress conditions. The core principle of ILT are then explained, including the role of key stress factors such as temperature, voltage, and load. And we also examine important acceleration models like the Arrhenius model, Eyring model, and the inverse power law model, which help predict product life under normal operating conditions. Different testing approaches, including step stress testing and constant stress testing, are can be will be introduced to highlight how stress is applied during experiments. Finally, we will review the main advantages and disadvantages or limitation of ILT along with an example case study to illustrate its practical application in real-world scenarios. All right, in section 4, I want to focus on test planning and sampling, which are critical steps in conducting effective reliability studies. I will begin by emphasizing the importance of proper test planning and clearly defining the objectives of the test to ensure meaningful results. Next, we will discuss how to determine an appropriate sample size based on statistical confidence requirements and various sampling methods, including random and statistical sampling, will be introduced to ensure uh, representative data collection, and we will also explore sequential testing and reliability demonstration testing, or RDT, as a structured approach for validating system performance. In addition, I will address test duration planning and efficient resource allocation to optimize time and cost. Finally, we will consider risk factors that may impact the testing process and highlight the importance of incorporating risk consideration into the overall test strategy. Now, each of these methods will use different or some similar formulation in different applications. So that's why I just ignore the equations and just introduce the concept here. Let me add a new student. All right. In section 5, I will focus on data collection, which places a crucial role in the accuracy and the reliability of the analysis results. And I will begin by highlighting the importance of data quality, as a reliable conclusion depend on the accurate and consistent data. Next, we will introduce the different types of data used in reliability studies, including complete data and censored data. An overview of censored data will be provided, covering right censored, left sensor, and interval sensor data, which occur in real-world testing scenarios. We will also discuss various data recording methods to ensure a proper documentation during testing. And finally, I will address the common data issues and emphasize the importance of data preprocessing to clean, organize, and prepare the data for effective analysis. Okay, in the next section, section 6, I will introduce the parametric methods which are widely used in reliability data analysis. I will begin by explaining the concept of parametric methods and the key assumptions underlying these models. Several important statistical distributions are then discussed, including the exponential, Weibull, and normal distributions. We already discussed in my previous lectures, but I will repeat a little this concept here. Each of which is commonly used to model different types of failure behavior, as you remember. And we will also cover parameter estimation techniques with focus on maximum likelihood estimation, or MLE, as a powerful and widely applied method. In addition, goodness of fit test also has been introduced to evaluate how well a chosen model represents the data. The section further explores reliability function estimation and hazard function analysis, which provide insight into system performance and failure characteristics over time. And finally, we will review the main advantages and limitations of parametric methods in practical applications, similar to the previous sections. In section 7, we will explore non-parametric methods which are useful for analyzing reliability data without assuming a specific statistical distribution. We will begin with an introduction to these methods and their importance in situations where model assumptions are uncertain or difficult to justify. And key techniques such as the Kaplan-Meier estimator and the Nelson-Allen estimator can be presented, and both of which are widely used for estimating survival and cumulative hazard functions. And we will also discuss life table analysis as a practical approach for summarizing reliability data over intervals. And furthermore, a comparison with parametric methods will be provided to highlight the difference in flexibility, assumption, and different applications. And finally, we will review again the main advantage of non-parametric methods along with their limitations in certain analytical scenarios. All right. In the final section, I will summarize the key concepts discussed throughout the lectures on reliability testing and data analysis. I will highlight the most important takeaways, and including the significance of proper testing methods, effective data collection, and the use of both parametric and non-parametric analysis techniques. I will also emphasize the practical applications of these concepts across various industries where reliability plays a critical role in ensuring product quality and system performance. Finally, I will open the floor for questions and discussions if you have, providing um, opportunity to clarify concept and explore the topic in more depths. And if there is any question, we will discuss here. All right, let me start to explain above objective of this lecture. So in this lecture, I will focus on understanding how reliability will be evaluated through systematic testing and data analysis. I will begin by exploring different reliability testing methods, including how tests are designed to assess product performance under various conditions. Then We move on to data analysis techniques where we learn how to interpret both complete and censored data sets. And this lecture also emphasizes the importance of selecting appropriate analytical methods, whether parametric or non-parametric, to accurately estimate reliability. And at the end of this lectures, inshallah, you will be able to connect testing strategies with data-driven decision making and apply this concept to your applications. So definitely for your assignment, you are using some basic data analysis, of course, and you will show me. Maybe you don't know this is a part of the data analysis, but during your presentation, we will discuss that. For example, you are using this method to analyze your data. Sorry. All right. Um, Reliability testing, as I mentioned before, plays a critical role in ensuring that product and system performance as expected under real operating conditions. By systematically evaluating performance, you can identify potential weakness and address them before deployment, similar to other methods. And this process significantly reduce the likelihood of failures and minimize associated risk, including safety hazards and financial losses. As I told you at the beginning of my lecture, the main objective of considering the reliability in the system is that to minimize the likelihood of failures and minimize associated risk. So moreover, reliable products lead to higher customer satisfactions and trust, while also helping organizations meet quality standards and regulatory requirements. Ultimately, reliability testing is very essential for delivering robust and dependent system in any field of energy, engineering. All right. Okay, in this lecture, I will cover several key topics that from the fundamentals of reliability testing and data analysis. I will begin with accelerated live testing, which allows you to estimate a product lifespan under increased stress conditions in a shorter time. I already developed ILT for one application, for example, in using the um, second-hand battery regarding the electric vehicles. But as I told you, the equations, the method can be a little bit different with other what you want to do for your application. That's why um, I'm just telling you the title of the concept, and after that, we will explore test planning strategies focusing on how to design effective and efficient experiments. We then examine data collection techniques, including how to handle different types of reliability data, such as complete and sensor data sets. Finally, we will discuss various data analysis methods, comparing parametric and non-parametric approaches to understand how reliability can be modeled and interpreted accurately. This lecture builds directly on the concepts covered in previous sessions. In earlier lectures, as I told you, I explored reliability modeling, including how systems can be represented using series and parallel configuration to evaluate the overall performance. We also studied probability distributions such as exponential and variable, which are essential for describing failure behavior over time. These fundamental concepts are very critical for understanding how reliability data can be analyzed in practice. In this lecture, I extended that knowledge by applying testing methods and analytical techniques to real reliability data, allowing us for more accurate predictions and informed decision makings. All right. In section two, second section, as I told you, we wanna talk about the reliability testing basics. So reliability testing is a fundamental process in reliability engineering that focus on assessing whether a product or system can perform its intended function consistently over time and under specified conditions or not. The main purpose of reliability testing is to identify potential failure modes before the product can be deployed in real world applications. And by doing so, you can improve the design, enhance product quality, and ensure long-term durability. And you can handle your systems properly, and the systems can operate without any problem. So additionally, reliability testings can provide valuable data that support informed decision making during the design and development stages, ultimately leading to more robust and dependable systems. Okay, reliability testing generally includes different types of tests, with live testing and environmental testing being two of the most important of this reliability testing. Live testing will focus on determining how long a product can operate before failure, either under normal usage conditions or through accelerated testing methods. And this help estimate metrics such as time to failure and overall lifespan and so on. And on the other hand, environmental testing evaluate how external conditions such as temperature, humidity, vibration, and pressures affect product performance, and it can make systems make some failure in the systems. Together, these testing methods provide a comprehensive understanding of how and why failure occur, enabling you to design more robust and reliable systems. All right. In reliability engineering, uh, testing methods are often categorized as a destructive or non-destructive method. And destructive testing involves pushing a product to failure in order to understand its limits and failure mechanisms. While this approach provides highly accurate and valuable data, the tested item cannot be reused. In contrast, we have a non-destructive testing, which allows you to evaluate the condition and performance of a product without causing any damage. Techniques such as ultrasonic inspection, X-ray analysis, and visual examinations are commonly used in this approach. Both methods are important as destructive testing helps identify failure thresholds, while non-destructive testing supports ongoing monitoring and maintenance without affecting usability. Reliability testings also can be performed either in the field or in a laboratory setting, each offering unique advantages. Field testing involve evaluating products under real-world conditions, which provides realistic insight into how a system performs during actual use. And however, it often includes variability and less control over external factors. On the other hand, we have a laboratory testing, which is conducted in a controlled environment, allowing you to isolate specific variables and perform repeatable experiments. This makes it easier to identify cause and effect relationships and conduct accelerated tests. In practice, both approaches are complementary, with laboratory testing offering precision and field testing providing validation under real operating conditions. All right. In reliability engineering, there are some key matrices. I already told you and defined all of these matrices, some of these matrices in reliability engineering. So key matrices such as mean time between failures or MTBF and failure rate are widely used to quantify system performance, and mean time between failures represent the average time a system operates before experiencing a failure, or making it particularly useful for repairable systems. So before that systems can be repaired, how long it will take time. So a higher mean time between failure generally indicates better reliability. On the other hand, the failure rate measures how often failures occur over a specific period of the time, typically expressed as failures per hour or cycle. And in the systems with a constant failure rate, these two metrics are inversely related, meaning that as a mean time between failures increases, the failure rate will be reduced. So we already discussed about this one, right? And I already show you this one, this equation. So understanding these metrics is very essential for evaluating and comparing the reliability of different systems. All right. So what are failure mechanism? Failure mechanism will describe the underlying physical, chemical, and or operational cause that lead to system breakdowns. And this can vary depending on the type of system and its operating conditions. Mechanical failures such as um, wear and corrosion occur due to repeated stress or material degradation over time, will be categorized as mechanical failures. Electrical failures may include short circuit or insulation breakdown, often caused by voltage stress or aging components. And thermal failures result from excessive heat or poor heat dissipation, which can damage sensitive components. Environmental factors like moisture, vibration, and contamination also contribute to failures. Additionally, human or operational errors such as improper use or insufficient maintenance can significantly impact reliability. Understanding these mechanisms is essential for designing more robust and reliable systems. All right. Uh, In this slide, I want to explain about reliability test standards. So this is also is important. I didn't mention the number because for each applications there are some different number of standards. And reliability test standards can provide structured guidelines and procedures to ensure that testing is conducted in a consistent and repeatable manner, for our system, for one specific system. And international organizations such as IC and ISO um, already develop widely accepted standards that are used across different industries. So, for your assignment report, also I'm very interesting to see that which standards did you use for to apply and implement your method for that specific application. So, um, in addition, industry-specific standards like MIL, STD, and IEEE standards define more specialized testing requirements, particularly in sectors such as defense and electronics. So these standards will help us ensure that products meet required levels of quality, safety, and performance. Compliance with such standards is often mandatory in industries like automotive, aerospace, and electronics, where reliability is critical. By following these established guidelines, engineering can ensure that their testing methods are both reliable and comparable across different systems and applications. All right. So let's come back to the ILT, Accelerated Life Test. I told you we will talk a little bit regarding this concept. So accelerated life testing, commonly known as ILT, is a method used to evaluate the reliability of products by subjecting them to higher than normal stress level. Now, the main idea behind ILT is to speed up the occurrence of failures so that you can observe and analyze them in a shorter period of the time. And this approach is particularly useful when testing products with long expected lifetime, where waiting for natural failures would take too long. By increasing stress factors such as temperature, voltage, or load, IRT will help predict how a product will behave under normal operating conditions and abnormal operating conditions. And this method is widely used in industries like electronics, automotive, aerospace, and material engineering to improve product design and reliability. Accelerated life testing is widely used because it offers significant advantages in terms of both time and cost. So instead of waiting for products to fail under normal operating conditions, which could take months or even years, ILT speed up the failure process by applying higher stress levels. And this can allows you to gather reliability data much more quickly, significantly reducing the overall testing time. In addition, ILT will help lower costs by minimizing the need for long duration experiments and repeated testing over extended periods. Behind time and cost savings, ILT also enables faster product development and helps identify potential design weakness early in the process, ultimately improving product reliability before it reaches the market. So this is summarizing the benefit of ILT methods. The core principles of accelerated life testing revolves around increasing stress levels to induce failures more quickly while still maintaining realistic results. In IRT, you can apply higher levels of stress such as temperature, voltage, or mechanical load than those typically experienced in normal operations, and we can see that system we can make operate continuously under this stress or not. However, it is essential that the underlying failure mechanisms remain the same so that the results can be uh, meaningfully related back to real world conditions. Acceleration models are then used to establish a relationship between stress and product life, allowing you to extrapolate data and predict performance under normal operation. Throughout this process, maintaining statistical validity also is very crucial to ensure that the conclusions drawn from the test are accurate and reliable. In accelerated life testing, stress factors are will be increased to speed up the failure process and better understand product reliability. And temperature is one of the most common stress factors, as higher temperatures accelerate chemical reactions, material degradations, and aging effects. Voltage is another critical factor, especially in electronic systems where increased voltage can lead to electrical overstress and insulation breakdown. And mechanical load is also important, as can be apply higher forces or stress, and this stress can cause deformation and eventual failure in mechanical components. In some cases, additional environmental factors such as humidity, vibrations, and pressures are also considered. By systematically increasing these stress factors, you can simulate long-term usage conditions in a much shorter time framework. All right. Um, Acceleration models are a fundamental part of accelerated life testing, as they provide the mechanical relationship between applied stress and the expected lifetime of a product. These models allow you to take data obtained under high stress conditions and extrapolate it to predict performance under normal operating conditions. Common models include the um, uh, Arrhenius model, which is used for temperature-related stress, and the Eyring model, which can account for multiple stress factors simultaneously, and the inverse power law model, which is often applied to mechanical and electrical stress conditions. And the key idea behind all these models is that increasing stress leads to faster failures and enabling quicker data collections and more efficient reliability predictions. So next week I will present some examples related to these models and methods. So we will see that how it can be applied in real world applications. The Arrhenius model is one of the most widely used acceleration models in reliability engineering, particularly for analyzing temperature-related failure mechanisms. It is based on the principle that many chemical and physical processes such as material degradation, corrosion, and diffusion occur faster at higher temperatures. In this model, the failure rate increases exponentially as temperature rises, which means that even a small increase in temperature can significantly reduce the lifetime of a product. The Arrhenius model is commonly used in industries such as electronics and materials science to predict how components like semiconductors and insulation materials will behave over time. By applying this model, you can estimate product lifespan under normal operating temperatures based on the accelerated test data. All right. So I wanna give you a breakdown for 10 minutes